Okay, everybody, welcome back. So, yesterday's lecture we ended with these two very basic facts. Um, as I said, more or less everything that follows comes from one of these two things in some way or repeated applications of these things. So, especially the product rule. Maybe let's start out with kind of one of the more basic sorts of questions. When it comes to counting is like how many M letter acronyms can be formed using the whole alphabet. So we are thinking of forming a string of letters here, right? These are acronyms, right? So they don't have to form recognizable words. So they contain M letters, and I'm allowed to use anything in the alphabet. Of course, I haven't made any rules here about not repeating letters. So, for instance, AAA, that's fine, right? BBBBB, if M is equal to 5 is fine. So I can have as many repetitions as I want. Of course, you might already be thinking about how to complicate this count by excluding certain things. You don't want, like, say, a string of 5 consecutive letters, right? So if it's a 5 letter acronym, you don't want A, B, C, D, E. There's various rules you could impose to make the count more difficult. Okay, but here we're just starting out, yeah, M letter acronyms using the whole alphabet. There's 26 total letters in alphabet. So 26 total letters. So how do I use this product rule here to figure this out? Well, each choosing an M letter acronym can be thought of as being done in sequence, where I'm choosing, at each step in the sequence, I'm choosing one of the 26 letters. Because of this thing where, the problem is set up in such a way that I'm not restricting myself, if I were saying, M letter acronyms using no more than 5 copies of the letter B, right? Then there would be some issues where my, 10th choice, for instance, it would depend on whether or not I had already chosen B 5 times, right? For instance. But here, in a simpler situation where all these are completely independent, like my 11th choice does not depend in any way on what I chose for the first 10 slots of this acronym. So in each slot, I have 26 choices, and that's it, right? So I have 26 choices for the first letter, 26 choices for the next letter, and so on. And for each choice, I have 26 options, and there are M choices, right? There are M slots, because this is an M letter acronym. So this is 26. Oh, I'm running out of ink. Let me pick a different pen. This is 26 to the M. Total M letter acronyms. Of course, you can adapt this how you like. If you wanted to think of like strings of numbers, right? Strings of digits, 0 to 9, and it's an M digit string. You could think about how many choices there are there. Can your choice begin with a 0 or not? Right? These are all the types of things you're thinking about when you're doing these kind of problems. Okay. Um, okay. What uh, what else? What else might I say here? Maybe let's do another example. Let's do let's see, valid phone numbers for the U.S. and Canada. Okay, so valid phone numbers. Under the North American numbering plan, a phone number has 10 digits. Okay, which is an area code, an exchange, a station code. So the 3-digit area code cannot begin with a 0 or 1. So this consists of an area code. So that's 3 digits. Um, an exchange, then a station code. But let's focus on this first. Area code cannot begin with a 0 or 1. So there's 2 digits the area code can't start with. Its second digit can be any number except 9. Second digit of area code can be any digit except 9. The exchange is 3 digits, and the station code is 4 digits. So that this is our total 10 digits here. What about the exchange? The exchange also cannot begin with a 0 or 1. So we have these 2 limits on the area code. The exchange code cannot begin with a 0 or 1. The station code can be any 4 digits. Okay. So, how do I deal with this? How do I deal with choosing this? So, well, let's choose the digits one by one, right? You'll notice that thinking of this process of constructing a valid phone number, there's no dependence here between the digits. There's no rule that says, well, if the first digit was 1, then the 7th digit in the whole string has to be blah, has to be odd or even. There's no kind of rule like that. So these are independent. I just have to track how many choices I have at each step. So area code cannot begin with a 0 or 1. So any of the other digits are fine. So that leaves me with 8 digits to choose the first digit of the area code. So I'm going to start with the first digit of the area code. Can't be a 0 or 1. So there are 8 choices for first digit of area code. Okay. So we'll say this block that I'm choosing here is the area code. So there's 8 choices for the first digit. For the second digit of an area code, it can be any digit except 9. So there are 9 choices. The third digit of the area code has no restrictions, so there's 10 total choices. This chooses my area code. Okay. Then multiplying that, the exchange code cannot begin with a 0 or 1. So again, the first digit of the exchange code is an 8. Or sorry, that's not the first digit. That's the number of choices of the exchange code is 8 because I have to exclude 0 and 1 here. The second and third digits aren't restricted in any way, so there's 10 options for both of those. So this is the exchange code. Of course, we're multiplying these all together because we're viewing the whole number as constructed in sequence, digit by digit. Okay, so now we have the station code, which has no restrictions whatsoever. So for each digit, we have 10 options. So this is the station code. And so, all taken together here, if you multiply this out, what do you get? You get 5,760,000,000. Okay. So, that's lots of valid phone numbers. Now, you might notice that this process and the way that it's done doesn't actually account for a couple of things. So note, we forgot something, right? So numbers like 411 and 911 are reserved in many areas. These are your like service codes, right? These are your service codes. But notice that the way we constructed these numbers, we could have constructed these because they didn't fail the rules that we set out here, right? For 911, does it begin with a 0 or 1? It can be any digit. The second digit can be any digit except 9, but that's not the second digit. That 9 is the first digit, right? Same thing here. This 411 would satisfy all these things. And so, how do we account for this? So we have computed the total number of valid phone numbers where we're not thinking about this. Let's now say we're going to exclude numbers that where the area code or the exchange code end with 11, right? End with 1 and 1, right? So let's ask the question, what is the number of valid phone numbers where neither the area code nor exchange code end with 1 and then 1. So, how does this work here? Well, what would I need to do in my previous count? So in the area code, what am I, how am I rewriting the number of area codes here, right? So the reason I kept these separate is so that if we were going to do something like this, we could see how to alter the area code count and the exchange code count, or even the station code if I put some restrictions on the station code. So the point is that all these could be thought of as counts taken separately, and then of course the total number of counts is multiplying them all together, again by the product rule. So for the area code, how am I going to do this? So uh, what would be the corrected number of area codes? The first digit is still the same. It can't begin with a 0, 1, and I know that the second digit can be any digit except 9. So um, let's count the area codes, right, the number of valid area codes in this way. The first digit is unchanged, or sorry, the first number of choices is unchanged. Then I'm multiplying that by what I've done here is it's the same count on the second and third digits, but I'm taking away one possibility for the second. It's that the second digit is 1 and the third digit is 1. So this is going to be still 9 times 10, but then minus 1. I'm just taking away the single possibility that I end with a 1 and a 1, right? 1 followed by a 1. So this is 8 times 90 is 720, minus 8 is 712. So there's 712 valid area codes if we use this rule. For the number of exchange codes, remember, exchange codes, the only restriction was the first digit can't begin with a 0, 1, so there were 8 choices, and then there were 10 choices for the remaining 2. Now, there's still going to be 10 choices for these, and then I'm going to take away a single option uh, for both digits, which is it can't be a 1 and a 1. It could be a 1 and anything else, or it could be anything else and then a 1, but it can't be a 1 and a 1. But there's only one option for that. So this would be 8 times 10 times 10 minus 1. So this is 8 times 99, or 800 minus 8. So this would be 792. So then the number of valid phone numbers here, I'm just going to insert this so I don't have to rewrite it. This would be 712 times 792 times, for the station code, this is just 10 times 10 times 10 times 10, 10 to the 4. So this would be 10 to the 4th, which is 5,639,040,000. So slightly reduces the number of valid phone numbers, but not by too much. Right? Could already service most of the world's population with this many digits following these rules. Okay. So there are 3 basic combinatorial problems, and the product rule and some rules are going to help us solve those. So maybe I should phrase it like this. Uh, Basic combinatorial problems. So let's say problem 1. How many ways are there to order a collection of indifferent objects? So, some examples. How many ways to arrange a standard 52 card deck via shuffling? This is like the total number of possible shufflings of a 52 card deck. Something I should mention as an aside, so any probability course you've already taken has already given you this warning. Um, Unfortunately, standard 52 card deck is a really, really good example or illustrative example for various combinatorial principles. This goes double for probability, right? So computing basic probabilities involving poker hands or some defined list of things or some defined list of properties that the hand must have for so a 5 card hand, 7 card hand, whatever. Um, you need to know this. Um, of course, you don't need to know any kind of obscure rules of poker or, well, even non obscure rules of poker. I will, anytime I'm asking you a question involving a deck of cards, I will explain to you exactly what I mean. So if I say, in how many ways can you deal a full house? I will explain what a full house is, so you don't need to know it. But this, unfortunately, if you're someone who doesn't know anything about the rules of poker or poker hands or anything like that, you're going to have to learn just a little bit, just because it's too good of an example to to pass up. So the main thing is just knowing the structure of the deck. So 52 card deck has 4 suits. Each suit has 13 cards. You have 4 types of face cards. We'll call the ace a face card, even though it doesn't have a face on it. So each suit has 4 face cards, which are Jack, Queen, King, Ace. Okay, like I said, I know that an ace doesn't have a face on it, but hey, it has the letters ACE in it. That's close enough, right? Also, it doesn't have a number value, although the number value indicated on the card is clearly 1. We'll ignore that, and the other cards start at 2 and count up to 10. Okay, so most of you have likely seen this, but just in case you haven't, this is the deal. So yeah, how many ways to arrange a standard 52 card deck via shuffling? This is a classic sort of question I could ask. How many batting orders on a baseball team? So how many possible batting orders on a baseball team? Is another example. How many ways are there to arrange 10 books on a shelf? All these. All these are examples of this sort of problem. So how let's pick the batting orders on a baseball team. So there are 9 players. This is standard, 9 players in a batting order. So 9 players take turns at bat here. Okay. I don't even need to label them or anything. I can just think of how to make this choice, right? So the point is, in a batting order, no player repeats. So it is truly like a distinct order. If you think of assigning an order, these are 9 players that need to bat in sequence. So using our product rule, since there's 9 players total, in the first slot of the batting order, the person batting first, there are 9 options. So 9 is the options in that slot. For the next slot, any player can bat so long as they haven't already had an at-bat opportunity. So the first player that batted is out, but all the remaining 8 players are valid options. So this would be 9 times 8 at the point of the second slot. For the third slot, anyone can bat on the team except the people who batted first and second. So there are 7 options, and then 6, and then 5, and then 4, and then 3, and then 2, and then the last one, well, there's only one more person left to bat. So by the time you get to the 9th batter, every other batter has been selected, so there is no choice at the last step. There's just a single one of them. Okay. Of course, you recognize this. You can rewrite this as 9 factorial. That is what this notation means here. So then, what is it that we are counting? Ordering a collection of n different objects. We call that a permutation of the objects. And the number of permutations of n objects is n factorial. This is, of course, directly from the product rule. So, but now we have a new thing. Whenever what we are being asked can be recast as asking about the number of permutations, or maybe counting the number of permutations helps count some other part of what you're doing, then this is at least a question you know how to answer. Okay, so that's problem 1. Let's ask another question. So this is problem 2. So problem 2 asks, how many ways are there to make an ordered list of k objects from a collection of n different objects? So how many ways are there to make an ordered list of k objects from a collection of n different objects? Okay, so examples of questions like this. So maybe one is, how many ways can a poll rank the top 20 teams in a college sport if there are 100 teams in the division, right? So how many ways can a poll rank the top 20 teams in some sport if there are 100 teams total? Okay. Now you might object and say, well, if we were going to rank like 100 teams, we're not just going to randomly rank them. We're ranking the teams we think are the top 20. So then we're thinking, well, that's not like a random thing. I actually know maybe like of the 100 teams, really there's only like 30 that are kind of in consideration for the top 20. So then, you could ask the same question where there are 30 teams total in your estimation to get maybe a more realistic number about the ways that you could do this, since you're not just doing this randomly. But again, these are things, if you can answer this question, you can answer that second question I asked very easily. Um, another example, how many ways can a band arrange a play or a playlist of 12 songs if they know only 25 different songs? Right. So how many ways can a band arrange a playlist of songs, uh, say 12 songs in length, if they only know 25 different songs? So you can pause the video at this point and see if you can answer these questions or start going about the answer of how you would handle this. So I'm going to try to apply the same reasoning that I used for the previous problem. And so what am I going to do here, right? The point is, if I have n different objects, so let's solve this. I have n different objects here. If I'm going to make an ordered list of k total objects from n different objects, how I would do that is, in my first slot, I have n choices, right? In my second slot, I can choose anything that's not the first choice. So I have n minus 1 options. In my third slot, I can choose any option that is not the first two things I chose. So n minus 2. And I continue this on until I have filled out k slots. When have I filled out k slots? When I reach n minus k plus 1. If you're wondering why this is n minus k plus 1 and not just n minus k, think about just the first three, right? If you only had 3 slots, it would be n minus 1, and n minus 2, not n minus 3. N minus 3 would be a fourth slot. So however many slots, it's not n minus k, it's n minus k plus 1. So this is the number involved. Okay. Now this, you might notice, is actually just n factorial divided by n minus k factorial. Sometimes you will see this written as the following. Sometimes this will be defined to be this number, p n k. You might see that in other textbooks, you might see that in other contexts, or you might have already seen that from either probability class or another class that's counting these sorts of things. But because products like this show up so frequently in combinatorial counts, there's some other notation we can use here that is a little bit instructive. So here's a couple definitions. So we are going to define x to the k falling is what we are going to call this. This is the falling factorial power x to the k falling. That's how I read that. Okay, this is the falling factorial power. So what do I do here? I begin with x, and then I fall to this x minus k plus 1 term. So this is x times x minus 1 times x minus 2, and so on down to x minus k plus 1. You could rewrite this using product notation as the product from 0 to k minus 1 of x minus I. You can see that these two things are the same. And as I said, we read this x to the k falling. We can also define the rising factorial power, where we put the bar over the k instead. This is the rising factorial power, or as we'll call it, x to the k rising. This is x times x plus 1 times x plus 2, and so on out to x plus k minus 1, which can be written in product form easily to see what it is that's actually going on here. This is just x plus I instead of x minus I. Okay. So notice a few things here using this notation. So take everything in here. I'm going to use clean sheet. So notice this, what we were calling P in K, which we wrote as n factorial over n minus k factorial, is actually just n to the k falling. But that could also be written as n minus k plus 1 to the k rising. And n factorial itself could be either written as n to the n falling or 1 to the n rising. You might complain that this is confusing because there's so many different ways of writing it, but this it's powerful because we're going to see how there are many natural ways where these falling and rising factorial powers show up in various counts, and knowing all of these relationships, like really searing these into your brain, will help you be able to manipulate some of those expressions that come out and finish some of these induction proofs, because you're already looking at the answer. You just have to rewrite it a little bit. So anyway, of course, just as the empty product is taken to have value 1, there are reasons that, for niceness sake, if you've never seen this before, the expressions n to the 0 falling, n to the 0 rising, 0 factorial, all of these are products having no terms, because when we multiply an expression by an empty product, we don't want the expression's value to change. We are going to set the value of all of these things to be 1. These might be called degenerate products or just empty products. All of these take the value 1. assigning these the value 1, this is a definition, and it's a definition that makes all the formulas work out nicely. So that's what I mean by niceness sake. If you're confused as to why 0 factorial is equal to 1, this is just a convention that makes all the formulas nice. If it wasn't equal to 1, we would have to alter some of the formulas and add cases, and it would just make everything uglier. So this works out far better. Okay. Now, another combinatorial problem. This could be called problem 3 here. It's how many ways are there to select k objects from a collection of n objects if the order of selection is irrelevant? So how many ways are there to select k objects from a collection of n objects if the order of selection is irrelevant? So examples are like how many different hands are possible in a game of poker. So how many hands are possible in poker? Second is, you know, say how many ways can I select, say like 5 numbered hats from a collection of, say, 20 such hats. So I have hats numbered, say, 1 to 20, and I'm wondering how many ways can I select 5 of those, right? How many distinct ways can I select 5 of those? Okay. So actually, we can solve this using both problems 1 and 2. Okay, so we can combine our solutions to problems 1 and 2 to get the answer. Which is what? In problem 1, we asked how many ways are there to order a collection of n different objects. Okay, so if we are talking about, say, k objects here, how many ways can those be ordered would be k factorial. So if I knew the number of ways to select k objects from a collection of n objects, then if I had that number times k factorial, that would be the number of possible ordered lists of k objects selected from the same collection of k objects. But I know from problem 2 that I know the number of ways to make an ordered list of k objects from a collection of n different objects. And so this, how many ways to select k objects from a collection of n objects, whatever number that is equal to n to the k falling divided by k factorial. So we are dividing by the number of possible orderings here for that reason. Because, again, thinking of it like this, if I knew what this number was, this number times k factorial would be the it would be different orderings of the total number of objects here. But then asking how many ways are there to make an ordered list of k objects from a collection of n different objects, that number would just be equal to n to the k falling. So then dividing by k factorial gives us this, and so rewriting this, of course, this would be n factorial over k factorial times n minus k factorial. Okay. This has another expression, or another symbol to denote it, which is this symbol that we read as n choose k. Because it counts the number of ways to select k objects from a collection of n objects. Okay. So, this is also known as the binomial coefficient. So this is a binomial coefficient. We'll talk about why that is a little later. But we read this as n choose k. Okay. Let's use this to do a couple of examples here. So like the number of possible poker hands. So a quick example. It's the number of possible poker hands here. Number of poker hands. Well, there's 52 total cards in a standard deck, and I'm choosing 5 of them if we're playing just standard poker here. So recall this was 52 to the 5 falling over 5 factorial, which is 2,598,960. Bridge is played with 13 cards, so this would be 52 choose 13. I'm just going to leave it like that. I'm not going to write how many that is, but it's more. It's a lot more. It's like 635 billion. Okay. Let's do another. So let's do suppose we need to travel m blocks east and n blocks south in a regular grid of city streets. Okay. How many paths are there to our destination if we travel only east and south? So how many paths are there to our destination if we only travel east and south? So at the end of our journey, we will have traveled m blocks east and n blocks south. So we could think of our path as a sequence. The sequence is B1, then B2, then B3, and so on. Then I have gotten to my destination at the n plus m step, where the b sub i's represent the direction we're traveling during the ith block, right? So the direction of travel during our transversing of the ith block. Okay, so then exactly m terms must be east, and the remaining n positions must be south. So m terms must be east. But how many ways are there to select m positions in this sequence to have this value? So then how many ways to choose m positions in this sequence to have this value? Well, there are m plus n or n plus m total. And I'm choosing m from those. Right? If I have chosen m positions to be east, the remaining positions all have to be south since I'm only traveling east and south. And so what is the number of possible paths? So all remaining positions must be south. Thus, number of total such paths is exactly n plus m, choose m, which is m plus m factorial divided by m factorial times n factorial. You might object and say, well, what was special about east in this way of doing it? Nothing. What if we had started with south? What would we have gotten? We would have gotten that the number of ways was n plus m, choose n, but this is the same, right? These are actually the same. So this is your first taste of these binomial coefficients having some kind of algebraic properties where there are different values involved here, but actually they're equal. We're going to see many, many, many examples of that. This is just like literally the very first taste. Okay, let's do another example. So this will be our third example of using these things. So consider a standard deck of 52 cards. So as I mentioned before, 4 suits. These are spades, hearts, clubs, and diamonds. Those are the suits. Okay, each has 13 cards in each suit. Each of the cards in a suit has a different face value. There's either a number between 2 and 10, so 13 cards in each suit. So the 13 cards have a value 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack, Queen, King, Ace. Okay. So the question is, how many poker hands have exactly 3 cards with the same face value? Okay, so how do I compute this? The answer is just like in our previous combinatorial problems where we thought about how to construct the thing. So, like, how, for instance, how to construct the valid phone number in our previous example. We think about how to construct this in a sequence, right? So, we think about how to construct such a hand in a sequence. So we break this down and then count the number of choices essentially at each of these simple steps in the sequence. And hopefully that provides us with a full enumeration of the possibilities here. So what do I do? So the first, I didn't specify which face value. So any of these are fine so long as the chosen one has 3 cards having the same face value. So maybe the 3 twos, maybe it's 3 tens, maybe it's 3 kings, right? 3 aces. Okay, so the first step is pick any of the 13 cards, right? So there's 13 choices there, right? We might write that for our own intuition as 13 choose 1. You know that there are 13 ways to choose a single card from 13 cards. So you might be tempted to just write this as 13. There's nothing wrong with that. That's perfectly fine. But this is just there is benefit in keeping everything in this n choose k notation for some of these problems. Okay, what is step 2? We need to choose 3 of the 4 cards in this deck that have this value, right? So choose 3 of the 4 cards in the deck to have this value. So for instance, say that I chose the 7 in step 1, right? There were 13 possibilities there. I picked 7. Okay, now that 7 is the thing involved here, I need to construct a hand with 3 sevens. There are 4 sevens in the deck total, right? There's the 7 of spades, 7 of hearts, 7 of clubs, 7 of diamonds, right? So 1 for each suit. I need to choose any 3 of them. It didn't say anything about what specific suits. So how many ways are there to do this? Well, there are 4 sevens. I'm choosing 3 of them. Okay. So that nails down 3 cards in my 5-card hand. And my step 3, I have a 5-card hand I'm constructing. I've nailed down 3 of them. They need to be the same face value. But the other 2 can be anything. Because, well, they can't exactly be anything because I said exactly 3 cards. So they can be anything except the other card, the 4th card in that set. So these need to have a different face value. So third, I need to pick 2 cards from the remaining. We had 52 cards. I have chosen 3 cards from one of these face values. The 2 remaining cards can be anything except one of those cards. Even the one I didn't pick is not allowed here. But there were 4 total. So 48 total is what I can pick from. So pick 2 cards from the remaining 48. That have a different face value. From the card selected in step 1. How many ways are there to do this? Picking 2 cards from 48. There's 48. Choose 2. Ways of doing this. So in total, this would be 13 choose 1 times 4 choose 3 times 48 choose 2. Because this constructs the hand. First step, I pick the card that I'm going to have exactly 3 cards match. So Jack, we'll say. Step 2, I have to select any 3 of those jacks. There's 4 choose 3 ways of doing that. Step 3, I need to pick 2 cards that are not jacks. So there's 48 choose 2 ways of doing that. There's a lot of ways of doing that. So then total number of possibilities here, 58,656. Okay. Now, if you know anything about poker, you might notice that in terms of poker hands, this is a count that without further differentiation is not going to be super helpful because in fact there are 2 major poker hands that worry about one card having exactly 3 copies of it among the suits. So there's 3 of a kind, which is you have 3 of one card and then the other 2 cards are just anything non-matching. And a full house, which is you have 3 of one card and 2 of another card. Okay. So note, this does not distinguish between a full house and 3 of a kind. Okay. So what if we wanted to make this distinction? So what is the number of ways to deal a full house? So 3 of a kind is 3 of one face value. Two non-matching cards. In the sense that they don't match any of these 3 and they also don't match themselves. And full house is 3 of one face value 2 of another, i.e. a pair. So you have 3 cards having the same face value and then 2 cards having the same distinct face value from the first 3 cards. Okay. So then, what if you were trying to think about dealing a full house? What's the number of ways of dealing a full house? So, the number of ways of dealing a full house, I'm going to do the same thing. I'm going to choose a card, choose 3 copies of that card from its 4 copies in the deck. Then, for the remaining 2 cards, we need to choose any of the remaining 12 cards here that are not the card first chosen. And then I need to choose 2 from those 4 cards. So this is 3,744. But then what is the number of ways of dealing 3 of a kind? The best way of thinking about this is 3 of a kind is 3 of one value, and then the 2 remaining cards do not match each other and they don't match one of these cards. So really, that's just the number of ways of dealing exactly 3 cards match, subtracting out the number of full houses. So you landed in the case where 3 cards have the same face value, but you're not in the case that the remaining 2 cards are a pair. That's what 3 of a kind is. So this is really number of 3 cards have same value minus number of full houses. But we've computed these two. Right, so this was 58,656 minus 3,744, which is 54,912. This is the number of ways to deal a hand having 3 of a kind. Now, quick question, is this the only way to do this count? Now, I'm going to put only way in quotes here because, of course, you might say, well, if you're claiming the count is correct, then obviously any other supposed way of counting has to at least match the number. It has to provide me with the same answer, which is true. And if you say that if it counts the same number, it's the same count, well, then yes, there's only one way. But that's not what we mean. What we mean is that is there a method for counting this, a process that seems on the surface different, and maybe the numbers involved even are different. Maybe we don't even use these binomial coefficient things, but it gets us the same answer. This is important in combinatorics because many combinatorial proofs involve essentially counting an underlying count in 2 distinct ways, and because they have to enumerate the same underlying objects, they have to be equal. This is a way of showing a lot of identities, and a lot of formulas and equations in combinatorics come from this idea of counting the same thing multiple ways. So the answer is no. So here's another way. Let's do this another way. So let's modify this strategy we had, counting the exact three cards having exactly the same face value. So in this process here, if we want to avoid this possibility of selecting a matched pair in this last step, why don't we replace this 48 choose 2 business? So going back here in our step 3, if I wanted to just directly modify this to avoid having to deal with whether or not we have a pair in the last bit, I can replace 48 choose 2 with the following. Why don't I replace it by 48 times 44 over 2? Well, what is this though? This is 48 times 47 over 2. I'm replacing this with 48 times 44 over 2. How do I, where does this come from? Well, the face value of the last card should not match any other card selected. And if we do this substitution, what do we get? We get 13 choose 1 times 4 choose 3 times 12 choose 1 uh, times, or this is, sorry, let's times, we'll do just directly 48 times 44 over 2. This is 13 times 4 times 48 times 44 over 2. If you check, this is 54,912, which is the same number we get here, and is a quicker way to do this. But you might ask, where does this division by 2 come from? In the binomial coefficient formulation, the division by 2 is just part of the definition of this binomial coefficient, this n choose k thing. Why do we divide by 2 here? So why divide by 2? Well, doing this last bit not using binomial coefficient, and again, I could rewrite this without even referring to these as binomial coefficients, because we have 13 choices for the first card, so that's just 13. 13 choose 1, yes, is equal to 13. It's really just 13. And then 4 ways of choosing the 3 cards I need. So this is really 13 here, and this is really 4 times this, which is 54,912. But why divide by 2? Where did I get this division by 2 from? Because the last 2 cards may be selected in any order. So I'm dividing by 2 to get rid of double counting the selections, because I could have selected them in any order and there's only 2 of them. So that's why I divide by 2. Okay, so this is, your first taste of how you can compute these 2 numbers in distinct ways. But there's nothing wrong with this count versus this count, right? As long as the count works, that's all we care about. Okay. So, moving on. binomial coefficients. Still haven't provided a reason for this. You have likely seen the theorem that these are named after, the binomial theorem. We will see that in just a bit. But first, I'm going to mention a bunch of identities that these have. And their identities, because the various algebraic properties they have is almost as important, maybe even more important for computation's sake, than like the specifics of where they came from. They have many, many different excellent properties that you are going to use so many times in this course you're going to get sick of them. So first, there's what I'll call expansion, which is just ever so slightly expanding on our definition of these binomial coefficients. So if n is a non-negative integer and k is an integer, then n choose k, this binomial coefficient, is n factorial over k factorial times n minus k factorial if k is between 0 and n, and it is 0 otherwise. Okay. So, of course, this makes sense because if we think about this in terms of choosing k objects, if k is bigger than n, how many ways are there to choose, say, 10 objects from 5 objects? Well, 0, right? When k is less than 0, this doesn't make so much sense, so just setting it equal to 0 is fine. Before I write the next property, now this is essentially just the definition with us making it so that we have, for these other values of k, we have nailed down exactly how this thing behaves. So this is, you could think about this almost as a definition, really, combined with our earlier comments on this. But now let's ask some questions about this. So first of all, if I select k objects from a set of n objects, that leaves this complementary collection of n minus k objects that are not selected. So then counting the number of subsets with k objects is the same as counting the number of subsets with n minus k objects. And so I've just proved in words the following property, which is symmetry. So again, n is greater than or equal to 0, k is an integer. I'm not going to restate that for all of these. N choose k is the same as n choose n minus k. Quick proof, maybe I'll just write it out. Well, you might call that the worst proof ever, right? It looks like I just turned this into words and said, "Yep, that's it. That's the proof." I just restated this in words, and that's the proof. But think about what I'm actually saying here. What I'm saying is that choosing k from n objects is the same as choosing n minus k from n objects, right? And the reason for this is, as I said in words before I wrote this down, if you have a collection of n objects and you select k objects from them, that's the same as selecting the remainder n minus k objects that you didn't select, right? So in this case, not selecting and selecting, you're selecting k, you're not selecting n minus k, but counting the number to select versus not select, this is going to be the same. This is why we call it symmetry. Okay, because a selection is simultaneously a non-selection. Selection of k objects is simultaneously a non-selection of n minus k objects, so counting the number of non-selections, counting the number of selections. This is why you get this. Okay. Now, let's think back to poker hands. Let's do a quick example. More poker hand stuff. Okay, so let's say, let's try to compute the number of 5-card hands that include the ace of spades. So we don't care about anything else, we just care that they include the ace of spades. Okay, so then how do I do this? I want to know the number of ways to select 4 cards from the other 51 cards in the deck. Right, that's really what I need to know. But we could also count the number of hands that do not include the ace of spades. So that's the number of ways to pick 5 cards from the other 51. That is 51, choose 5. But every poker hand either includes ace of spades or doesn't. So those things we can add together. So basically, how do I want to think about this? So I need the number of ways to select 4 cards from the other 51 cards in the deck. Well, this is 51, choose 4. But then, what's the number of hands that do not include ace of spades? So your entire hand is chosen. All 5 cards are chosen from the remaining 51. Okay. So notice that the number of ways to select 4 cards from the other 51 cards, this is the same as the number of 5-card hands that includes the ace of spades. Because your one selection of the ace of spades, you're nailed down there. There's only one option. So then the remaining 4 cards, there's 51, choose 4 ways of doing that. Okay. So this second thing is actually equal to the first. That is what I'm counting here. Number of hands that do not include the ace of spades, of course, is 51. Choose 5. But every hand either includes ace of spades or does not. Therefore, another way of thinking about this is to make any hand of 5 cards. Number of ways to do that's 52, choose 5. So this includes every possible 5-card hand. But then any hand either contains ace of spades or doesn't. The number of hands that do not include the ace of spades is 51, choose 5. Added to that, the number of ways to include or to have 5-card hands that include the ace of spades, this is 51, choose 4. And that should exhaust the possibilities because 5-card hand either contains the ace of spades or doesn't. So 52, choose 5 should be the same as 51, choose 5 plus 51, choose 4. What we have just shown in a specific case is the following thing. This is known as addition. N choose K is the same as N minus 1 choose K plus N minus 1 choose K minus 1. The proof of this is essentially unpacking this example that we just did for generic N and K. Okay, so literally just unpacking what we said for the specific case of, say, the ace of spades, considering now doing the same sort of partitioning for generic n and k. That is the proof of this addition formula. So, and like I said, we can also prove this by just directly passing to how these things are defined. So we'll do that next time. We'll prove this, continue on with binomial coefficient stuff, and then move right along. These binomial coefficients are an extremely important part of combinatorics. These are going to show up all over the place constantly, pretty much for the remainder of the course. The good news is that you're likely already fairly familiar with these and have used these before, so this shouldn't be too unwieldy or overwhelming. But anyway, that is the deal for now. We'll continue on our combinatorial stuff next time. So like I said, yeah, we'll finish all this binomial theorem stuff and then do some multinomial stuff before moving on. So I will see you all tomorrow.